Hi, in the following video I'm going to try to illustrate in Maya some mathematics concepts, namely vectors and matrices. More precisely, I will talk about the Cartesian coordinates and the right-handed axis system, how to add and subtract vendors, unit vectors, finding the length of a vector, dot product, cross product, and matrices. Cartesian coordinates. The Cartesian coordinates is a system that allows us to locate points in the space. You can see here the one-dimensional Cartesian coordinates. It is named after René Descartes, a French mathematician and philosopher who invented the concept. Then later were developed the 2D and 3D Cartesian coordinate systems. So let's see how that's working in Maya. So here we can see the x-axis, y-axis, and z-axis. Here in the bottom left we can see how it actually works in Maya. So we are talking about what they call a right-handed Cartesian coordinate system. I'll talk about it in a moment. So the important thing is that it allows me to settle a point to locate it in the space. So for example here, if I see the channels, I see that it's in the point x4, y1, and z minus 2. So z minus 2 because this is the positive set, and from here it's negative set. So I want to say I wanted to move it to positive set, so I just have to change it to 2, or and that would be it. So we can see that now it's positive. Yeah, so left, if we could use the left-handed coordinate system, that would be z would remain the same, but x and y have changed their orientation. So x now whatever. So for example here x would be -4 and y would be -1. In this case it doesn't change because this is just a representation, but Maya keeps always using the right-handed coordinate system. It is not important what you use, but you have to know what you are using. Vector addition and subtraction. So the result of adding up two vectors is equivalent to adding up the individual components of the vectors. So let's work one example here. So I take my pencil here and let's define, sorry about that. So let's define a vector A that will be 6, 3, 0, and a vector B that will be 3, 7, and 0. So I can work out I plus B is equal a different vector C, that is 6 plus 3 is 9, and 3 plus 7 is 10. Okay, so I expect a vector 9, 10, 0. So let's work out this in Maya. So I come here, what I will do is first I will load to the memory this function that I have defined to help me create my vectors on the screen. So I execute it, so I have it in memory, and now I'm going to work out the example. So I define the two vectors as we had them, and I show them on the screen. These are my two vectors. You can see that I have my ball indicating the head, and I'm going to work out the vector C, adding their components. So let's see how much is this. The vector 9, 10, 0, 9, 10, 0. That's what we expected, and I'm going to show it in the screen. Okay, and this is the resulting vector A plus B. So what I'm going to do here is to show how would be adding up graphically as a means of validation. So I have my vector A, and I'm going to duplicate vector B and put it on the head of vector A, and here we go. So this is the resulting vector, goes from the tail of A to the head of the projection of B. Okay, perfect. So I'm going to delete this now and work out an example for the subtraction. So the subtraction of vectors A minus B will be a different vector that I'm going to call D, and will be 6 minus 3 is 3, and 3 minus 7 is minus 4, and 0. So I expect a vector 3 minus 4, 0. So I come here, and again I define exactly the same vectors and show them on the screen, and a new vector that is A minus B component by component. Right, I see 3 minus 4, 0. Is this what I was expecting? Yes, it is. Okay, perfect. And I'm going to show it on the screen. So this is my resulting vector A minus B. Okay, and let's validate this graphically. So to do so, I'm going to do a trick, that is to calculate and show the vector minus B. So this vector, this is the vector minus B, and I'm going to translate it, sorry, all of it. So take it all, and I'm moving it from the head of the previous vector, and we can see how it works. Now it's exactly the same from the head and from the tail to the head. So that's about the subtraction. Right, unit vectors and length of a vector. So before understanding unit vectors, let's explain how to calculate the length of a vector. So the length of a vector is sometimes called magnitude or norm of a vector. So it's given by these formulas. This is for the 2D case, and this is a 3D case. So, but let's see where this comes from. So it comes really from Pythagoras, right? Because if I have a vector R here in the, sorry, this is a mess, Y and X coordinate. So if this is delta Y and this is delta X still here, right? This bit here. So this formula comes from applying Pythagoras, realizing that this is a triangle right angle, right? So this is the hypotenuse. Okay, so, and let's work an example here of the magnitude of a vector. So if I have my vector A, that is 6, 3, 0, can calculate its module by square root of 6 to the power of 2, that is 36, plus 3 to the power of 2, that is 9. It is right 45. Okay, this is the correct 45. Okay, so we have calculated the length of a vector, and this is useful for normalizing a vector. So a unit vector, going back to the unit vectors, unit vector is a vector whose module is 1. So this module, this vector R, his magnitude is not 1, it's square root of 45, that is 6.71. Right, so it has some interest to calculate a vector that is in the same direction than R, but its magnitude is only 1. So this is how we calculate it. we divide by the magnitude of the vector. So for example, if we calculate the unitary vector for A, or our example could be just to divide by square root 45 its components that are, we say, 6, 3 and 0. So this would be a vector that is unitary. And let me just mention the Cartesian vectors that are unitary vectors that are conventionally used to so any vector can be expressed in terms of its unitary vectors, right? So so they could be defined as here. So let me put here the Cartesian coordinates, and here we have x, sorry, y and z, and the unit vector I, j, and k. Okay, and any vector can be expressed under this. So for example, this vector that is u is 0.89, 0.45 and 0 can be also expressed in terms of the Cartesian vectors as 0.89 I plus 0.45 j plus 0 k. Okay, so let's see this in Maya. So let me delete this, and so what I do here is I have my vector 6, 3, 0, and I show it on the screen, right? I import this math module so that it allows me to calculate the square root to calculate the module. So I calculate the module, and it's 6.7. That is what I had worked out in the other screen, and I normalize it now. So I divide by its module and show it, and here we have our unitary vector is 0.89, 0.45. That's correct. And here we can see what we mean. No, so we have a vector A that is in this direction. We have a vector in the same direction, but only one, module 1, right? So that's what I meant. And why is interesting the unitary vectors? Because sometimes we are only interested on the directions, and it's much less expensive in terms of computing time to do simple operations on unit vectors rather than big numbers. So it's much memory saving. The dot product of two vectors results in a number, a scalar, not another vector. So the interesting thing about the dot product is that we can find it through these two formulas as seen here. So for example, this one comes from this would be this figure. So we have a vector S and a vector R, and this is the projection of R over S, and here we have our angle beta, right? So the dot vector of S by R could be module the length of S by the length of R by cos beta, right? But we can also work it from this definition and the components in the Cartesian axis. So this is the final formula for it, so we can simply multiply and add it component by component. So let me explain it in an example. So for example, if we have our two vectors, so we have vector a 6 3 0 and b b, what is the b 370, we can say, okay, yeah, AV equals 6 by 3 plus 7 plus 0. So this is 18 plus 21, that is 39, right? Then we have calculated the dot product, and then we have the other, then we can calculate the module of A, that is a square root of 36 plus 9, and we can calculate too the module of B, that is square root of 9 plus 49. So this is square root of 51, and this is square root of 45, and so we are able to calculate from this formula. We are able to get cos beta equals 39, 45. So we have been able to calculate the angle between two vectors. That is a great thing to do. Yeah, let's see this in Maya. So in Maya, okay, let me remove this, and I'm going to, again with my vectors, I'm going to show them. I'm going to import math again because I need the square root to calculate the modules 6.7 and 7.6, and then I calculate the dot product just multiplying the components. So here we go, the dot product is 39 exactly, and then I calculate the angle and convert it to degrees. Okay, okay, so just why is useful this dot product. So this dot product has many applications, but for example has applications in collision detection, working with the projection of one vector over the other, or for calculation of the intensity of illumination in the Lambert law, or on the detection as seen here, to detect the parts that are detect the angle of a vector, and according to that angle, if it's bigger or smaller than 90 degrees, we show it or don't show it. So for internal calculation, the cross product or vector product of two vectors results in a third vector. So we have a formula here, very similar to what we had in this scalar vector. In this case, the mod for determining the module is rs sen beta. So let me write the case. So we have a vector r and a vector S that form an angle, and here, there, right. So okay, and then we have another way for calculating the actual vector, that is multiplying its Cartesian coordinates, and this is what we call determinants. There's another way of expressing this that that I like, that is just say R by S equals to, we can put here the Cartesian coordinates J, K, and well, we can work it Rx, Ry, Rz, Sx, Xy, Sz. Right, this would be a more general way of expressing the same. And so we can work an example now. So let's say we have a vector A6, 3, 0 and a vector V, 3, 7, 0. So we can calculate I by B by expressing AJ K, and here we can put 6, 3, 0 and 3, 7, 0. We have to work out the determinant. It will be I by 3 by 0 by 3 by 0 minus 7 by 0. So this will be 0 plus J, plus J, and then we take 6 by 0, we cross it, minus 3 by 0, it will be 0 again, and K, in this case, will be 6 by 7 minus 3 by 3. Okay, and this is 42 minus 9. So in the end we have a resulting vector of 33k. Right, so that's the result of this. So we can see something interesting, that is that the resulting vector it's a vector that is totally perpendicular. So we had this is xy, and we had our two vectors here under this plane, and the resulting vector is coming this way, totally perpendicular to this plane. So this is a very interesting property of the cross product. So let's see this in Maya. So let me remove this first, and I define again my vectors and show them. I import the math just in case and calculate their modules, and I have calculated here the determinants and the resulting product. Let's see, 0, 0, 33, that's what we expected. Here determinant x is 0, determinant y is 0, determinant z is 33, and let's show the vector. Okay, so here let's hide this, and here we can see the result of this dot product. So we have two vectors under the xy plane, and we have the resulting product vector that is only in the k coordinate, right? Only has z coordinate. So yeah, that's it. And yeah, some applications for the cross product. It's very interesting to calculate normal to surfaces, right? Or because of this property that results in a perpendicular plane. So for matrices, what I'm going to do is to create a cube here, right? It is called pcube1. So then I have this script. So we're going to import commands, Maya commands, and you can see that the name is pcube1. So with this command we get this, we will define this matrix, that is the transformation matrix of this cube. So if I print it in the screen, well, in the script editor what we get is a matrix, but we can see that it's all in just one row, so it's very hard to read. So what we're going to do is this trick, that is to divide it just for presentation purposes on the screen. We're going to divide it row by row so that the presentation is more on it. So we define it like this and show it in the screen, right? So here what we have is a transformation matrix for the cube that we can see that has an X row, Y row, Z row, and transformation row. So we can play with this and see how it changes when we translate, scale, or rotate the cube. So for example, if I come here and translate the cube in this coordinate, for example, we can see here in the channel box that is changing. So we're going to say 1, let's say 2, so that it's clear. So we have translated it, and what we do now is repeat this to see how the transformation matrix has changed. It was 1 1 1 identity here, and now we have a 2 here in the translation row. In the Z coordinate we have a 2. If we translate, it's quite straightforward. If we say in the 5 in the X and repeat it, so we can see that it's now 5 and 2. Okay, that's easy, that's understandable for the translation. We'll go back to the original position and then we can play with the rotation. So if we just rotate it with the key E, you can rotate it here in the X coordinate, and we repeat operation, and we can see that now it's a more complex matrix, right? Okay, we return it to the original position, and we can also play with the scale. So let's make this cube twice as big in every coordinate and run the transformation matrix, and well, we can see that now we have something similar to the identity, but it is now with 2 2 2 and 1 for the translation. And yeah, that's more or less it.